the limit as x approaches 0 of sine of x over x equals 1, which is a very well-known limit called the fundamental trigonometric limit. I'm going to be proving it here using the geometric proof, which involves the squeeze theorem. You can't just use L'Hopital's rule to find this limit, and the reason for this is because we would need to know the derivative of sine of x in order to apply L'Hopital's rule for this limit. And it turns out that to find the derivative of sine of x using the limit definition of the derivative, we need to know the limit as x approaches 0 of sine of x over x in the first place. So here's what we do. We first draw the unit circle and consider three areas. There's the triangle fully contained within the unit circle itself, the sector within the unit circle, and the larger triangle which extends outside of the unit circle. The larger triangle is a right-angled triangle with a base of length 1, which goes from the origin to the point 1, 0 on the coordinate plane. These areas all lie within the first quadrant, as the diagram suggests, so we are only considering values of theta in between 0 and pi over 2, non-inclusive for now. So the first area is the triangle fully contained within the unit circle. Notice how I drew the shapes with the same colors as the ones drawn in and around the unit circle, just so it's more clear which area I am talking about. This triangle would have a base of 1 because the unit circle has a radius of 1, and a height of sine of theta because the height of the triangle is just the distance between the x-axis and the point on the unit circle. The y-coordinate of the point on the unit circle is just sine of theta, which is why the distance between the point and the x-axis is sine of theta. The area of the triangle is 1/2 base times height, and we've established a base of 1 and a height of sine of theta. So the area is 1/2 times 1 times sine of theta, and this just simplifies to 1/2 sine of theta. Before I cover the area of the sector contained within the unit circle, I want to talk about the formula for the area of a sector when we use radians as the measure for angle. The area of a sector is essentially the area of the circle multiplied by the portion of the circle the sector takes up. So this would be pi r squared, which is the area of the circle, multiplied by theta over 2 pi, since 2 pi is the angle of a full circle in radians, which would make theta over 2 pi the portion of the circle the sector takes up. If we simplify this expression, the factor of pi and pi in the denominator cancel out, and the area just turns out to be 1/2 r squared times theta. So the area of the sector contained within the unit circle is 1/2 times 1 squared times theta, because the unit circle has a radius of 1, so r equals 1. This simplifies to 1/2 theta, which is the area of the sector. Now let's consider the area of the larger triangle that lies partially outside of the unit circle. The triangle has a base of 1 because the unit circle has a radius of 1, and the height of the triangle is tangent of theta, and here's why. The triangle is a right-angled triangle, and the definition of tangent of theta is opposite over adjacent in a right-angled triangle. If we look at the diagram of the triangle with theta being the angle labeled as theta, the adjacent side, which is the base, has a side length of 1, as we've established earlier. The opposite side is the one drawn in red, which is the height of the triangle. Since tangent of theta is equal to opposite over adjacent, and adjacent is equal to 1, this means tangent of theta is equal to opposite over 1, which is equal to opposite. This means the opposite side has a side length of tangent of theta. Since the base is 1 and the height is tangent of theta, the area of the triangle is 1/2 times 1 times tangent of theta, which equals 1/2 tangent of theta. So why did we consider these three areas? It's so we could derive an inequality which we could use the squeeze theorem with. In the first quadrant, when theta is between 0 and pi over 2 non-inclusive, we can clearly see that the area of the smaller triangle can't be bigger than the area of the sector for all theta values in the specified domain. The area of the sector, in turn, can't be greater than the area of the larger triangle, which is the one that lies partially outside of the unit circle. So the area of the smaller triangle is less than or equal to the area of the sector, which is, in turn, less than or equal to the area of the larger triangle. This means we can take the areas from the three shapes and form the inequality 1/2 sine of theta is less than or equal to 1/2 theta, which is less than or equal to 1/2 tangent of theta, for all 0 less than theta less than pi over 2. Since we're trying to find the inequality, we can use for the limit as x approaches 0 of sine of x over x. We would like the middle part of the inequality to be sine of theta over theta, where we're just using the variable theta instead of x. If we divide all sides of the inequality by 1/2 sine of theta, we end up with the inequality 1 less than or equal to theta over sine of theta less than or equal to tangent of theta over sine of theta. We didn't need to change the direction of the inequality, because this inequality is only for theta values in between 0 and pi over 2 non-inclusive, and sine of theta is always positive for these theta values. This means we're dividing by a positive value, so we don't need to change the direction, which we would only need to do if we're dividing by a negative value. We can also be sure that we're not dividing by 0, because sine of theta is always non-zero in the specified domain. We can rewrite tangent of theta over sine of theta as 1 over cosine of theta, because if we take tangent of theta over sine of theta, and rewrite tangent of theta as sine of theta over cosine of theta, we get a complex fraction. We can simplify this by multiplying cosine of theta in both the numerator and denominator, and end up with sine of theta over sine of theta times cosine of theta, and the sine of theta in the numerator and the sine of theta in the denominator cancel out, and we just end up with 1 over cosine of theta. Since we want sine of theta over theta instead of theta over sine of theta in the middle part of the inequality, we should take the reciprocal of all sides of the inequality. The reciprocal of 1 is still 1, so the first part of the inequality stays the same. Theta over sine of theta becomes sine of theta over theta, and the reciprocal of 1 over cosine of theta is cosine of theta. Since we're taking the reciprocal of positive values, we can use the property that if a is less than or equal to b, and a and b are both greater than 0, then 1 over a is greater than or equal to 1 over b, which is why we need to flip the inequality signs. So the inequality becomes 1 greater than or equal to sine of theta over theta greater than or equal to cosine of theta. What we're really doing here is applying this property twice for the inequality we have. And of course we can be sure that all three terms are positive, because for the first term, 1 is clearly positive. For the second term, theta takes on possible values between 0 and pi over 2, which is positive, and sine of theta is positive for these theta values. So theta over sine of theta must be positive. And for the third term, cosine of theta is also positive for the given theta values, so 1 over cosine of theta must also be positive. We can rewrite the inequality as cosine of theta less than or equal to sine of theta over theta less than or equal to 1 by reordering the terms, and we end up with the same inequality. And of course this is only true for 0 less than theta less than pi over 2. So we now have an upper and lower bound for sine of theta over theta, which we can use to apply the squeeze theorem. But these are only for theta values between 0 and pi over 2, which means they are only for values greater than 0. So the inequality for this domain is going to be used for when we approach 0 from the positive side. We also need to show that this inequality is true for values less than 0, so we can determine what happens when we approach 0 from the negative side. So let's first write down the inequality we already have. Cosine of theta less than or equal to sine of theta over theta less than or equal to 1, which we already know holds for 0 less than theta less than pi over 2. We want to show that this inequality is true for negative pi over 2 less than theta less than 0. If 0 is less than theta, which is less than pi over 2, then negative theta over 2 is less than negative theta, which is less than 0, which means if we plug in negative theta into the expressions with theta values in between 0 and pi over 2 in the inequality, we are effectively determining what happens to these expressions when theta is in between negative pi over 2 and 0, which is what we want. The idea here is to show that the inequality still holds even for the negative theta values. We can use the negative angle identities, sine of negative theta equals negative sine of theta, and cosine of negative theta equals cosine of theta to simplify the expressions once we plug in negative theta. If we plug in negative theta into the first expression in the inequality, we end up with cosine of negative theta, which equals cosine of theta using the negative angle identity for cosine. So when we plug in negative theta for theta in cosine of theta, we still end up with the same expression. If we plug in negative theta into the expression sine of theta over theta, which is the middle expression in the inequality, we get sine of negative theta over negative theta. Sine of negative theta is equal to negative sine of theta by the negative angle identity for sine, so the expression becomes negative sine of theta over negative theta. The negatives cancel out, and we just end up with sine of theta over theta, so if we plug in negative theta for theta in sine of theta over theta, we still end up with the same expression. The rightmost expression in the inequality is 1, which is a constant, so it stays the same no matter what the value of theta is. So we don't have to worry about it. So if we plug in negative theta for theta into each of the three expressions, we still end up with the same expressions. This means the original inequality, which was true for theta values in between 0 and pi over 2, is also true for theta values in between negative pi over 2 and 0, because when we plug in negative theta for theta values in between 0 and pi over 2, we're really plugging in theta values between negative pi over 2 and 0. And when we do that, we can see that the expressions all stay the same, which implies the original inequality holds for theta values in between negative pi over 2 and 0, non-inclusive. The limit as theta approaches 0 of cosine of theta is equal to 1 if we plug in 0 to cosine of theta, and the limit as theta approaches 0 of 1 is just equal to 1 because 1 is a constant. So we have two functions that bound sine of theta over theta from above and below respectively in the interval containing 0, which is the value we're trying to find the limit at, and the two functions have the same limit as x approaches 0. This means we can use the squeeze theorem. So let's review what the squeeze theorem is very quickly. So let's say we have an interval I containing the point A, which is the point we're trying to approach the limit from, and g of x, f of x, and h of x are functions defined on all points in the interval I, except for possibly the point A itself. We don't need the functions to be defined at the point A, because if it were for f of x, which is the function we're trying to find the limit for, then we could just plug in the value A, and we wouldn't even need to use the squeeze theorem in the first place. If g of x is less than or equal to f of x, which is less than or equal to h of x for all x and I except for A itself, and the limit as x approaches a of g of x is equal to the limit as x approaches a of h of x equals L, then the limit as x approaches a of f of x is equal to L. This is basically saying that if we have two functions, g of x and h of x, which bound the function from below and above, respectively, in the interval containing the value we're trying to find the limit at, and the limit of g of x and h of x at x equals a is the same value, then we can conclude that the limit as x approaches that value of f of x is the same as the limits for g of x and h of x. So we know that cosine of theta is less than or equal to sine of theta over theta, which is less than or equal to 1 on the interval between negative pi over 2 and pi over 2, excluding the point theta equals 0. And we have the limit as theta approaches 0 of cosine of theta equals 1, and the limit as theta approaches 0 of 1 is equal to 1. This means by the squeeze theorem, we can conclude that the limit as theta approaches 0 of sine of theta over theta is equal to 1. So since the limit as theta approaches 0 of sine of theta over theta equals 1, we can use another variable x and infer that the limit as x approaches 0 of sine of x over x is equal to 1, which is what we were trying to prove.